the equation for a plane in space. And remember that equation was something like a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. We also discussed the equation for a sphere in space. So a sphere in space had this equation. And, for the plane in space, the point x naught, y naught, z naught, that was just a point that belonged to the plane. And a, b, c, that was the entries of the normal vector for that plane. For the sphere, you remember x naught, y naught, z naught was the center of the sphere. It was the point in the center, and then r is the radius of the sphere. So that's just a review. But in here, in this section, we're going to talk about explicitly defined surfaces. And I already kind of said this, but if z is some kind of function of independent variables x and y, that's what we mean whenever I tell you the surface is explicitly defined. We can also talk about implicitly defined surfaces, and we'll do maybe some of those at the end of class if we have time. And later this semester we're going to talk about parametric surfaces. And so there's different kinds of surfaces. Explicitly defined surfaces are the easiest because we just have an explicit function telling us about the coordinates. So let me just graph a few of these for you. Like, let's look at this one that says z equals e to the power negative x squared minus y squared. And I'll try to do that here. Okay, so this graph of e to the power negative x squared minus y squared looks like this. It's kind of like a three-dimensional kind of normal distribution, like a bell. It's a nice bell shape. Let's do another one. If I want z equals x squared minus y squared. Get kind of a potato chip kind of shape, or maybe it looks like a horse saddle if you're into riding horses, right? Whenever you do your homework and you're actually playing around in MATLAB, I want you to try some different functions and just see what those shapes look like. And then the last thing we'll do is this x squared plus y squared really quick. Show you what that looks like. So this shape, the x squared plus y squared, this is what we call a paraboloid, because if you look at it from any side, the shape along the bottom is a parabola, right? But this is sort of three-dimensional, so we call it a paraboloid to indicate that it's just a three-dimensional shape that's like a parabola in some way. Okay. Now, new vocabulary word. A trace is the curve that you get if you take one of these surfaces and you slice it with a plane, right? So wherever that plane slices your surface, the curve that would be left on the plane is the trace. So, first example says, what is the trace of this function in the YZ plane? And I should make just a quick note that so far this semester, whenever I've been drawing stuff in space, I've been drawing my XY plane first, and then I draw this little axis that goes sort of through the board forward to you, and I've been labeling this Z. Normally the convention, whenever you're using like MATLAB or GeoGebra or anything else, normally the convention is actually that we call up the Z direction, and then how we label the other axes is I can't even draw the axes. I'm trying to make that go through the origin. That's close enough. How we normally label the other axes is really the same as what I've been doing under just a rotation. Do you see how you could take this xy plane and then just kind of rotate it, and then you'd have the same axes? And so neither one of these is wrong. It's just the same thing under a rotation. Okay? And so however you want to orient this or however you want to rotate it is just up to you or up to convention. But whenever we graph these surfaces, normally we use z as the up direction. So normally we would use this kind of convention. So whenever I ask the question, what is the trace of this in the YZ plane? Well, then I'm talking about this plane that's like flat with the board. And the surface is in 3 dimensions, so it's going to come in and behind, it's going to come out of and behind the board. But if we could just use this flat plane to slice this 3-dimensional surface, or this 2-dimensional surface that's living in 3D space, that's what we would call the trace. And to find this, we just have to consider that in the YZ plane, there's one variable that's constant. In the YZ plane, we're saying that x is equal to 0. Everywhere inside the YZ plane, x is equal to 0. So what I'm going to do is I'm just going to take this, and I'm going to set x equal to 0. And then I get this function, z is equal to y squared. And you know what that function looks like, hopefully from like algebra class. But in the YZ plane, z equals y squared would look like this. And so that is my trace. You know the surface z equals x squared plus y squared, that is this paraboloid surface. But if you sliced it in this plane, the trace of it would be this parabola. Does that make sense? Okay, so my next question then says, what is the trace of the same paraboloid in the plane where z is equal to 4? So if I told you z is equal to 4, that actually specifies a plane in space, that's parallel to the xy plane, but it's just translated 4 units up from the xy plane. And again, the trace is really easy to find. I just have to take this equation and then set z equal to 4, and I get the equation x squared plus y squared equals 4. Or I could even say x squared plus y squared equals 2 squared. Does anybody recognize what that is? It's a circle. This is a circle that is centered at the point 0, 0 for my x and y coordinates, and it has radius 2. That's just the equation for a circle. So, again, the paraboloid looks like this. If you sliced it with a horizontal plane with coordinate z equals 4, and here's 4 right here on my axis right here, on my z-axis. So if you slice that, you should see a circle as the trace on that plane. Okay. New question, what is the trace of this? Of z equals x squared minus y squared in the xz plane? Well, in the xz plane, what variable is constant?
What?
Y. Yeah, in this xz plane, y is constant and y equals 0. Yeah. So if I just set y equal to 0, the trace is going to be z equals x squared, so the trace is going to be a parabola. So here's my xz plane, and then this parabola would look like this. I'm going to plot this in MATLAB too. So x squared minus y squared. Okay. So again, the vertical axis is the z-axis. And so if I slice this along the xz plane, the trace is going to be this parabola that's sitting in the saddle like that. Okay? Then what would be the trace of z equals x squared minus y squared in the yz plane? So the yz plane, what variable is constant? X. And x is equal to 0. So the trace of this is going to be z equals negative y squared. So here's my yz plane. The trace is going to be this downward facing parabola, because the parabola z equals negative y squared. And so again, going back to my MATLAB picture, you can see that if I sliced this with a plane this way, that the trace would be this downward parabola that sits underneath the saddle. Okay. So new definition, new vocabulary word. I might sometimes use this. If I ever ask you for the level sets of a function, the level set of a function where z is a function of x and y, so I would say x and y are my independent variables, z is my dependent variable. The level set, or a level set, would be the set of points where a point is an x and y pair, coordinate pair. It's a set of points that give the same value for z, or the same value for your function. So another way to remember this is that a level set is just the trace for a plane where you set z equal to a constant. I would write the level set is the same thing as the trace where z is equal to a constant. So I might ask you, what is the level set for z equals x squared minus y squared when z is equal to 4? Right? So I'm just setting the value of my function equal to a constant, in this case 4, and we would get the equation 4 equals x squared minus y squared. And this is the equation for a hyperbola. Which means, if you were looking at this little saddle shape and you slice it horizontally at the plane where z is equal to 4, what you would see as the trace is a hyperbola. And since the way we define a level set is just a specific kind of trace, we would say that the level set at z equals 4 is a hyperbola. Now, new definition. A topographical map is a collection of all of the, well, I shouldn't say all, that's dumb. It's a collection of some level sets of an explicitly defined surface. So if I wanted to make a topographical map for the function z equals sine of x, lots of typos here, sine of x plus cosine y, what I need to do is just choose a bunch of values for z. Like I might say 0 is equal to sine x plus cosine y, and that's going to make a trace. And then I would say 1 is equal to sine x plus cosine y, and that would make a trace. And then I would try -1 is equal to sine x plus cosine y, and then I might say 1/2 is equal to sine x plus cosine y, and then maybe -1/2 is equal to sine x cosine y, and 1.5 and -1.5, and just choose as many level sets as you want. And then whenever we collect all of those together, that's what we're going to call a topographical map. So first let me graph again what this looks like if I have z equals cosine x plus, no, sorry, it was sine of x, right? Sine of x plus cosine y. We'll see that surface in 3D here, okay? And so I'm trying to make a topographical map of that, and my favorite 2D graphing tool is Desmos, so I'm going to go to desmos.com, and then I'm going to start making those level sets, like 0 equals sine of x plus cosine y. That's pretty cool. And then I'll do the 1 equals sine of x plus cosine y. And then I'll do 1/2 equals sine of x plus cosine. And then I'll do -1 equals sine of x plus cosine y. And then I'll do -1/2 equals sine of x plus cosine y, and then I'll do 1.5 equals sine of x plus cosine y, and then let me also do -1.5 equals sine of x plus cosine y. Okay. So this is what I would call a topographical map, and if I wanted to make this specifically the map of just what I plotted on MATLAB over here, my bounds I used on MATLAB were x equals -3 to +3 and y equals -3 to +3, so I would have to zoom in a little bit to make this match up exactly. And that is almost perfect. Let me do this again. -3 to +3 and -3 to +3. There we go. So this is the topographical map here of what we were looking at here on MATLAB. So this hill, that little peak, is going to be right here in the center of all these level sets. That's where the maximum is going to be. And then going down these level sets means the function is going down in value. And then as you turn and go this way, the function is going to be at its lowest points on either side here. It looks like, since this green is the same level set as this green, it looks like the function is at its maximum, and then it decreases in value, and then maybe it starts going back up once it reaches that green again. And so this is kind of how you have to read these topographical maps, and that corresponds to this. You know, it's high, and then it goes down, and then it starts to go back up a little bit, you know? So, so like if I search topographical map, I don't know. This is just a Google image search. And I have no idea where this is, but if you're looking at this map, you know, you can kind of tell where this little region is steeper because more of the lines are closer together. And regions where it's flatter are going to have not very many lines, you know. Every line means the elevation changed by like 20 feet or whatever. So these points that are sort of the center of all these topographical level sets, the centers of all these level sets are probably like peaks of mountains. And I mean, y'all probably have read topographical maps before, so maybe I'm just being a little redundant here. So, a few more things. If you see this in your textbook talks about like a cylindrical surface. A cylindrical surface is just a really boring kind of sheet-like 2D surface. Like, it is a surface, but it's really boring. You can get a cylindrical surface if you make z a function of x, where y would be a free variable, or if I make z a function of only y, and I let x be a free variable. And you do get surfaces, they're just not very exciting. Like, if I have the surface y equals, sorry, let me say that again. If I have the surface z equals sine of x, and I don't make z a function of y, I'm just letting y be a free variable, it's just not as exciting. You just get these sort of flat sheets, you know? There's not really any more information in the surface than just in a normal graph of sine of x. But this is what your textbook calls a cylindrical surface. You can think of like a cylinder, how we're used to thinking of cylinders, as being like a cylindrical surface of a circle. Like if you just took a circle and then you let one variable be a free variable, then you would just have a cylinder. So that is that, if you ever see that vocabulary word. And then a quadric surface is an umbrella term that means any surface that can be given by this equation. So this equation is a x squared plus b y squared plus c z squared plus d xy plus e xz plus f yz plus g x plus h y plus I z plus j equals 0. So that's a long equation. All of these capital letters, A, B, C, D, E, F, G, H, I, J, all of the capital letters are just constants. Those are just coefficients, like 1, 2, 3, etc. And anything you can make with this equation is called a quadric surface. And these are kind of like conic sections in a way. Remember talking about conic sections last semester. A conic section was anything you could make with this equation. Right? A conic section was anything you could make by changing the value of the capital letters in that green equation, A, B, C, D, E, F. And we showed how in a two-dimensional plane, these conic sections were just curves that were either circles or ellipses or parabolas or hyperbolas. Those were the types of conic sections you could get by manipulating that equation. Well, by manipulating this blue equation, we're going to get what we call quadric surfaces. And I'll try to make some of these for you, but these are the main types of quadric surface. You can either get an ellipsoid, a hyperboloid of one or two sheets, an elliptic cone, or an elliptic paraboloid, or a hyperbolic paraboloid. I'm going to try to make as many of these as possible. I'm going to use my less favorite graphing calculator because it's just a little bit faster than using MATLAB. And I'm going to type in ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus abcdef g x plus hy plus iz plus j equals 0. Ta-da. Okay, so it gives me a lot of these sliders where I can adjust the values of a, b, c, d, e, f, g, h, i, j, and my goal here is to change the values of these sliders until it gives me a ellipsoid. I honestly don't even see anything really yet. So I have some work to do here. I want to make these products 0. I also want to make those 0. And then I want to make j negative. And I think that should do something. Yeah, there we go. Okay, it has to be very negative. I want it to be large. Okay, I'll just zoom in instead. Okay, so this right here is what we call an ellipsoid. It's an ellipsoid because it's kind of like a sphere, but if you were to take the trace of it along any plane, it would not really be a circle, it would be an ellipse, right? And so I can sort of mess with the dimensions of it by messing with the coefficients a, b, and c. But an ellipsoid is just kind of like a sphere but stretched in some direction, okay? That's what we mean by ellipsoid. Then let me try to make a hyperboloid of one sheet and see how that goes. I'm going to make one of these negative. There we go. Perfect. Okay. So this is called a hyperboloid of one sheet. And you can kind of see from this trace that you can see the hyperbola happening. You can also see from this trace there's a hyperbola. But from this trace, it's an ellipse, right? Like if you made a slice with certain planes, it would give you an ellipse. And so this is why we call it a, well, I guess we call it a hyperboloid of one sheet. Let me try to make a hyperbola of two sheets and see if it's possible with my setup. Maybe if h is a large negative number. Yeah, perfect. Okay. So this is a hyperboloid of two sheets. And I say it's a hyperboloid of two sheets because you can see that there's two parts to it, right? Like it gets sort of pinched off somewhere between negative 50 and 5. So hyperboloid of one sheet, if you just pinch it right there, boom, hyperboloid of two sheets. So that's what we mean by those. An elliptic cone, I probably can't do because I think you have to have really precise control over the what do you call it? The coefficients here. But an elliptic cone is just sort of like a double cone that meets at a vertex, but then if you take any slice of it, the slice would be an ellipse. And you know, a circle is an ellipse. And so technically like a sphere is an ellipsoid just with the same radii in every direction. An elliptic cone, like a normal cone that we're used to, is also an elliptic cone. It just happens to have the same radii in both directions. An elliptic paraboloid, I can graph in MATLAB really quick. I can just make x squared plus y squared, and then I'll just divide y squared by 3, right? Just to show you that if I take any sort of level set of this paraboloid, it would be an ellipse. Okay, but the other traces would make parabolas, hence elliptic paraboloid. Hyperbolic paraboloid I can also make in MATLAB, and we've already done this today. But if I do x squared minus y squared, we call this a hyperbolic paraboloid because from some traces you get a parabola, and from other traces you get a hyperbola. So those are your quadric surfaces. And quadric surfaces are kind of like the three-dimensional analog of conic sections. Whenever we are doing these quadric surfaces, notice that this equation is an implicit equation, not an explicit equation. I'm not telling you that z is a function of x and y. Instead, I'm giving you just this implicit relationship. And so these surfaces are not explicitly defined surfaces. These surfaces I would call implicitly defined surfaces. Like an ellipsoid is an implicitly defined surface. And an ellipsoid doesn't represent a function because for any inputs x and y, there's actually two different outputs for z. And what we normally say in algebra for a function is a function can only have one output for a given input. And so like an ellipsoid does not represent a function, so it's not an explicitly defined surface.